The first example we're going to be looking at is called the coin change problem. It is one of the classic optimization problems in all of DSA. So I'll read out the problem statement formally and then we'll look at examples and stuff. Given a set of denominations d1, d2, so on up to dm and an exchange value e, the coin change problem tasks us with finding the minimum number of coins of said denominations required to make rupees e. You're allowed to assume that there are infinite number of coins of each denomination. So if that was a little too technical, look at the example here. So you have denominations rupees 1, 3, 5 and 7. These are the only denominations of money available with you, and you have infinite number of coins of each denomination. Now you are expected to pay someone rupees 19. Now obviously there are multiple ways of making up this amount of money, rupees 19, using the available denominations. You can choose 19 coins of 1 rupee each. You can choose 6 coins of 3 rupees each and 1 coin of 1 rupee. You can choose 5, 5, 5, 3, 1. There are numerous possibilities, out of which the question asks, find the minimum number of coins required. So if you look at this example, the minimum number of coins would be 3. It would be 7 rupees plus 7 rupees plus 5 rupees. Any other combination of denominations you use will take more than 3 coins. So what the coin change problem asks us to do is, you have a bunch of denominations, you have infinite supply of coins of each denomination, and you have a target amount which we call the exchange value. So you have to pay money equal to the exchange value using as few coins as possible, and the problem asks you to find what are the minimum number of coins required. So that is the statement of the coin change problem. As you say, I used the word minimum, so you already know it's an optimization problem, and also it's easy to see that the solution to this problem for rupees 19 in some way depends on the solution for rupees 18, which again depends on the solution for rupees 17 and so on. And when I say depends on, I'd like to clarify one thing. I'm not saying the solution for coin change problem with these denominations with 19 is simply an extension of the solution for 18. It's not like you solve the problem for 18 rupees and then you just add a 1 rupee coin. That may or may not be the case depending on your exchange value and depending on your denominations allowed. But in some way it depends. So you take whatever answer you got for 18 and you try adding a 1 rupee coin. You check that one, and then you take a totally different combination like 775. You compare those and then you see which is minimum and you pick that. So the point I'm trying to drive home is, whenever you have a DP problem, and when I say overlapping or interdependent solutions, I don't mean that the solution for a bigger problem is simply an extension of the solution for a smaller problem. It uses that smaller solution, performs some comparison, some operation, and then arrives at the final solution for the bigger problem. In that actual operation, the smaller solution may or may not be used, but it comes handy for your comparison purposes. That is what I mean by overlapping subproblems. So now you know that this is an optimization problem and there is an overlap of subproblems. So there is an interdependence between the smaller problems. So we know this qualifies as something that can be solved using dynamic programming. So I'll quickly explain the same thing in a mathematical format. This is a screenshot of a slide from Kandappan sir's PPT. So you have C1, C2, Cm. This is the notation he's chosen to use for denominations. Exchange value is EV. Your objective is to minimize the summation NCI. NCI is the total number of coins of the Ci'th denomination. So NC1 refers to how many coins you have used of denomination C1, NC2 how many coins of C2, and so on. So the objective is the total number of coins across all denominations must be minimized, and your constraints are summation NCI into Ci less than equal to EV, meaning your total money, the total amount made by the coins, which is expressed as number of coins of a specific denomination into that denomination. So for example, 2 coins of rupees 7 and 1 coin of rupees 5 would be 2 into 7 plus 1 into 5. So the NCI represents the number of coins, 2 and 1 respectively. Ci represents the denomination, 7 and 5 respectively. So the weighted sum of all of that, or I'm sorry, like you take the product of the number of coins and the denomination and you add up that, it should be equal to EV ideally, or if not equal, it should be as close as possible. That is obviously the constraint. And of course the number of coins chosen should be greater than equal to 0. You cannot have -1 coins and all that stuff. So that is the explanation of the coin choice problem, and I'll quickly clarify why this is a less than equal to and not an equal to, because ideally you want to make as many rupees as your exchange value, but supposing your denominations are not supportive of that. Let's say the denominations given to you are rupees 246 and I ask you for an exchange value of 21 rupees. Your exchange value is an odd number and you don't have a 1, 3, 5 anything in your denomination, so the closest you can get is a 20. That is why we have a less than equal to here. So to summarize, coin change problem is you have some denominations, you have a target value, you have to make up that target value using these denominations with the minimum number of coins possible. That is the problem statement.